Happy day, everyone. This is just going to be some tips on how to solve some of the problems on the first 2 pages of the Thermo pack. So let's get right to it. The first question is asking, write the equation for the combustion of a mole of acetone. Well, that's pretty easy. You just have to make sure that when you balance your reaction that it is 1 mole of acetone. So if it's 2 moles, for example, so just keep that in mind as you work the problems out, that you would actually divide everything, for example, by 2 if it were 2 moles. And so then you're going to have fractions as your coefficients, but that's totally fine. Okay, so that's kind of something I wanted to tell you about that. This is kind of something to make note of here. It says the liberation of. What does liberation mean? It just means freeing of. So in other words, they're talking about releasing of this 1790 kilojoules, and you know if it's releasing, that must be exothermic, so what sign should you be attaching? And that's what they're asking you for the delta H notation. So literally just the number, but with the sign and the units. The next one says, what would be the quantity of heat evolved if 25 grams of acetone undergoes combustion? It's a lot like the bottom of the first page of the notes, where you're going to start with the grams, you're going to convert your grams to moles, and then what you're going to do is you're going to use this value right here to be able to help work out kind of like stoichiometry, a little bit like stoichiometry, where you're attaching an energy value to a certain amount of moles. Okay, so that question, as well as number 3, is similar, so is number 4. And so let's come down to number 6, because I wanted to do this one with you. So this one is supposed to be done in class. So it says, what's the reaction for the combustion of butane? It's a hydrocarbon. Okay, well, they're giving us what butane is anyway. So we know it's C4H10 plus O2. We're burning it, oxygen gas. And we know when you react O2 with TO, always creates co-anho, co-anho, co-anho. So we've got CO2 gas and we have our H2O liquid, very typical of a combustion reaction. Okay, so now in this case, and typically it's the gas that actually burns, but this is okay, it's saying liquid. So I want to balance it, so I'm going to put a 4 in front of my carbons here, and then I can move on to my hydrogens. I can see that I have 2 on this side, so let's put a 5 in there. Well, on my right, I have 8 and 5, which is 13, but on the left, I have 2. The rule is change odd to even. So I'm going to change the 5, and instead, I'm going to make it a 10, so odd to even. When I do that, well, that changes this so that it's 20 hydrogens instead. Well, that changes my carbons. Instead of 4 carbons, now it's 8 carbons. So let's put that 8 in there. And now let's figure out our oxygens. So now I have 16 and 10, which is 26. Well, that means that it must be 13. Okay. So based on the way that this reaction is written, this is for burning 2 moles of C4H10 because that is what the coefficient is. Now I can keep it exactly that way, okay, but you just have to be careful when you go to do the next part. It says the energy released per mole of butane that undergoes combustion is 322 kilojoules. So that means that the delta H is equal to a negative 322 kilojoules for every 1 mole of the C4H10 of the butane. It says that butane lighter released 475 grams of CO2. How much energy did it release? Okay, so we know that we're looking for kilojoules or joules, but since we already know unit in kilojoules, right here, we can just use kilojoules. Okay, so I've got my 475 grams of the CO2. Okay, let's look up the molar mass of carbon dioxide. So it's 32.00 plus the 12.01. So I'm going to get 44.01 grams per mole of the CO2. So now I'm in moles of CO2. Okay, now I want to make sure that you understand that energy, when you talk about energy, energy is something that can be transferred, but it's not necessarily, I don't know how to phrase this, but it's not necessarily assigned to one particular thing. It's assigned to the entire reaction. So unless you're looking at the heat of formation, for example, of a particular substance. So there are actually 2 ways that you can go about this. Okay, one way is if I look at this reaction, I can say that the delta H for this particular reaction of this reaction as it's written is double the negative 322, which means it's a negative 644 kilojoules. Now, I'm not going to say per mole because it's not really for a mole of anything. It's for 2 moles, okay? So I can leave it that way and say that's my delta H for this reaction, for these reacting with each other and creating those products. So I could use that. Let's use that. Well, if I do, then I'm going to say that for every mole of CO2, nope, for every 8 moles of CO2, it's negative 644 kilojoules. Okay, so all I'm going to do is I'm going to multiply and divide that, and when I do, I get 869 with 3 6 figs kilojoules. Okay, yes, it's negative, but they're kind of asking us for the absolute value because they're saying how much energy was released. So I don't necessarily need a sign unless they're asking me for it in this case. Okay, now what's the other thing that I could have done? Well, I could also use this right here, but that means that I would have to reduce my equation down. So if I do that, I divide everything by 2. So then I would get a 1 and a 6.5, a 4, and then back to a 5 on this one. Okay, fine. Well, my last step, how would it be different? Well, instead, it would be negative 322 kilojoules, which is what they gave us, but that would be for 4 moles of CO2. Well, if you do that, you will get exactly the same answer. Okay, so either way that you'd want to do that, you'll get the same answer, and let's move right on to the next question. Okay, so this next one says that they want us to write the equation for the formation of NO3, okay, the delta HF. So I need to make sure that you remember this. So the definition of the heat of formation is the amount of energy absorbed or released for the formation of 1 mole of a substance from its elements in their standard states. Elements in their standard states, if we say standard states, what we're talking about is the delta HF is equal to 0 kilojoules per mole. So in other words, in order to make it, it's already in nature, so it already exists in nature, and we didn't have to actually put anything together to make it. And these are all the elements in their standard states. Now, don't forget, you've got your diatomics in their phase, whatever phase that they're in, that would be 0. Okay, so this first one says formation of NO3. You have to be careful. Okay, so the question is, what does it take to make NO3? What does it take to make NO3? Well, a lot of times people will say, I don't know, NO2 and O2, but you want it from its elements in their standard state. So what 2 elements make up NO3? N and O, but remember, diatomic, so it's N2 and O2. Okay, so then we're going to balance it. So we need a 2 there, and then we need a 3 there. And then that leaves us with a 2 in front of the nitrogen. Now, the only thing is, this again says that that's for 70.9 kilojoules per mole is actually for 1 mole of making NO3. And in this case, we have 2 moles of NO3. So what I can do is I can either reduce it or I can change my number, okay? Whichever way you want to do it. So if I stick to this positive 70.9 kilojoules per mole, then what I need to do is I'm going to need to switch this and make this a half, make this 3 halves, and make this 2 halves, which is simply 1. Okay, and so now it's written for 1 mole. So just keeping that in mind, and then you would do the same thing for B. Okay, now number 8. It looks harder than it actually is. They are saying using your table, find delta H for the following reaction, and using the numbers from number 7. So all they want you to really do is use this number right here for N2O5. That's the delta HF of N2O5. You know the delta HF of NO3. So you know N2O5 and you know NO3. So the only thing you have to look up is on your thermo chart is you just have to find NO2, and then all you're going to do is products minus reactants, and that's going to give you your delta H, theoretical delta H value. That's all they're asking you for. Okay, number 9. So in this, products minus reactants, pretty easy. Just don't forget, please, please don't forget. It's product plus product minus reactant minus reactant. Otherwise, you have to do the sum of the reactants if you're going to add them. So just make sure if you have 2 reactants, you have to subtract. Do not forget that, okay? All right, and the last thing I wanted to talk about is for number 10. So I'm going to do letter A with you. It says that it's methanol vaporizing. So I'm going to go with CH3OH. What is vaporizing? Well, that means that it's turning from a liquid to a gas. And so all I'm going to do is products minus reactants. So once you have your reaction set up, you can simply do products minus reactants. So let me take a look at the thermo chart here. So I found them right here. I've got my negative 201.2 for the gas and negative 238.6 for the liquid. And so all I'm going to do is products minus reactants. So negative 201.2 minus a negative 238.6, which gives me positive 37.4 kilojoules. Okay, and that's, again, that's for the reaction. That's for the reaction. It is for mole, for 1 mole. And this last one down here, the standard heat of formation is delta H equals this value. The standard heat of formation of this one is positive 80.3. Calculate the enthalpy change in the reaction. You already know that hydrogen is 0, so simple product minus reactant. All right, and hope this helps you. Have a great day.